Hi learners! For today, we will estimate the square root of whole number to the nearest hundredth. And we will plot irrational numbers on a number line. And it was based on Mathematics 7, Quarter 1, Module number 7.
This is from LRMDS Bulacan. Credits to the author, language reviewer, content editor, illustrator, and layout artist of this module.
Hi math lovers! Are you ready? Let's learn! Have fun! Because mathematics is fun!
What I need to know.
This module provides varied activities that will enhance your understanding about the principal roots, irrational numbers, and a number line. At the end of this module, you are expected to approximate square roots, estimate the square root of a number to the nearest hundredth, and plot irrational numbers on a number line.
What I know. Turn your module to page 4. Let's answer the pretest. Tell whether the given radicals are rational or irrational. Write your answer on the space provided. Which of the following is the principal root of the given radical? And circle the letter of your answer. What's in?
An irrational number is a real number that cannot be written as a simple fraction. Irrational means not rational. In our given example, 1.5 is equals to 3/2. We have here a ratio, meaning this is rational. In our second example, we have pi with a value of 3.14, 15, 9, and so on, or non-terminating decimal. That is not a ratio, that is irrational.
Rational number can be written as a ratio of two integers. 1.5 is rational because it can be written as the ratio 3/2. 3 is rational because it can be written as ratio 3/1. 0.333 and so on, or 3 is repeating decimal, is also rational because it can be written as the ratio 1/3. Let's try irrational numbers. But some numbers cannot be written as a ratio of two integers. They are called irrational numbers. Pi is a famous irrational number. It has a value of 3.14, 15, 9265, and so on. We cannot write down a simple fraction that equals to pi. The popular approximation of 22/7 is equal to 3.14, 2857, 1428571, and so on. Is close but not accurate. Another clue is that the decimal goes on forever without repeating, so we can tell if it is rational or irrational by trying to write the number as a simple fraction. Let's try this given example. 9.5 can be written as a simple fraction like this. 9.5 is equal to 19/2. So, it is rational number, and so it is not irrational. Let's try this given example. 1.75 can be written as a simple fraction like this. 1.75 is equal to 7/4. This is rational number. Another example, 0.001 can be written as a simple fraction like this. 0.001 is equal to 1/1000. And this is an example of rational number. Another example is pi. Pi is a famous irrational number. People have calculated pi to over quadrillion decimal places and still there is no pattern. The first few digits look like this. How about this example? The number e, or Euler's number, is another famous irrational number. People have calculated e to many decimal places without any pattern showing. The first few digits look like this. The next example is the golden ratio. The golden ratio is an irrational number. The first few digits look like this. Let's try this last example. Many square roots, cube roots, and others are also irrational numbers. Let's have our example. Square root of 3 is equal to 1.73, 20, 50, and so on. And square root of 99 is equal to 9.94, 98, 7, and so on. But square root of 4 is equal to 2, which is rational. And square root of 9 is 3, which is also rational. So, not all roots are irrational. What's new? To identify whether a principal root is a rational or irrational number, determine if the radical is also perfect to the n power or not. If it is, the root is rational. Otherwise, it is irrational. Let's try these given examples. Square root of 25 is equal to 5, and this is rational. Next is square root of 64. We have 8, and this is rational. But square root of 35 is equal to 5.9161. It is irrational. Last is square root of 80. We have 8.9443. It is irrational. If a principal root is irrational, the best you can do for now is to give an estimate of its value. Estimating is very important for all principal roots that are not root of perfect n power. The principal root of the given radicals below are between two integers. Find that two closest integers. We have square root of 7. 4 is a perfect number before 7, and 2 is its principal square root. 9 is the next perfect number after 7, and 3 is its principal square root. Therefore, square root of 7 is between 2 and 3. Find the two closest integers. Square root of 60. 49 is a perfect number before 60, and 7 is its principal square root. 64 is a perfect number after 60, and 8 is its principal square root. Therefore, the square root of 60 is between 7 and 8. The square root of 234. 225 is a perfect number before 234, and 15 is its principal square root. 256 is a perfect number after 234, and 16 is its principal square root. Therefore, square root of 234 is between 15 and 16. Estimate the square root to the nearest hundredth. Square root of 13. Square root of 9 is the nearest perfect square to square root of 13. The principal roots of square root of 9 is 3. For the fractional part, for the numerator, get the difference of the two whole numbers 13 and 9. 13 minus 9 is equal to 4. And for the denominator, multiply the principal root of 3 by 2. 3 times 2 is equal to 6. For the next step, divide the difference 4 by the product of 6, and the answer will be the decimal value. 4 divided by 6 is equal to 0.66, and so on. The principal root of square root of 13 is approximately 3.66. Let's try this given example. Square root of 130. 121 is a perfect number before 130, and its perfect square root is 11. Square root of 121 is 11. Subtract 121 from 130, and the difference is 9. The principal root 11 is multiplied by 2, and the product is 22. Let's divide 9 by 22, and that will be the decimal value of 0.409. The principal root of square root of 130 is approximately 11.41. Now for our last example, we have the square root of 54. 49 is a perfect number before 54, and its perfect square root is 7. Subtract 49 from 54, and the difference is 5. The principal root 7 is multiplied by 2, and the product is 14. Divide 5 by 14, and that will be the decimal value of 0.35. The principal root of square root of 54 is approximately 7.35. Let's answer this. Turn your module to page 10. Estimate the square root of the whole number to the nearest hundredth. Use your solution to navigate through the maze. Mark the dot by using your pencil. In math, a number line can be defined as a straight line with number placed at equal intervals or segments along its length. The numbers on the number line increase as one moves from left to the right and decrease on moving from right to the left. The number line can also be used to represent fraction, decimals, positive and negative numbers. Writing numbers on a number line makes comparing numbers easier. Numbers on the left is smaller than the numbers on the right of the number line. Now let's have example number 1, square root of 11. Let's use this number line. By estimating the square root of 11, we can locate the decimal value on the number between 3 and 4, but it is approximately near to the whole number 3. Now we have example number 2, negative square root of 20. Now let's use this number line. By estimating the negative square root of 20, we can locate the decimal value on the number line between negative 4 and negative 5, but it is approximately near to the whole number negative 4. Now let's answer this. Turn your module to page 12. By approximation, solve for the square root of the given whole number to the nearest hundredth. Then, plot the given radical numbers on the number line. What is it? Now, let's estimate the square root of a whole number to the nearest hundredth.
Exponent can be used to show that a number has been multiplied by itself one or more times. You can write 2 times 2 times 2 as powers, such as 2 to the third power or 2 cubed. Likewise, you can write 4 times 4 as 4 squared, and 5 times 5 times 5 times 5 as 5 to the fourth power. A power has two parts, a base and an exponent. In the power 2 cubed, the base is 2 and the exponent is 3. In our illustration, we have 2 thirds. 3 is our exponent and 2 is our base.
A perfect square is the square of a whole number. The number 4 is a perfect square because 4 is equal to 2 squared. The number 5 is not a perfect square because there is no whole number that can be squared to get 5. You know that 25 is the square of 5 because 5 squared is equal to 25. You can also say that 5 is the square root of 25. The square of 5 is the length of the side of the square with an area equal to the number. Approximating square roots can be determined by finding the nearest perfect square root of the given. Subtract the radicand. The difference will be the numerator. Multiply the principal roots to the nearest perfect square root by 2. The product will be the denominator. Divide the numerator by the denominator. That will be the decimal value to the nearest hundredths. The key is to familiarize yourself to the whole numbers with perfect square root. Irrational number is a number that cannot be expressed in the form a over b, where a and b are integers and b is not equal to 0. Now, let's plot irrational numbers on a number line.
Numbers graph on number line. The first step in graphing any group of numbers on a number line is figuring out their order. Start with the smallest number up to the largest number.
Let's have example number 1. Arrange square root of 2, square root of 5, and pi on the number line. Now look at the number line. Notice how the red tick marks aren't on the whole number tick marks. All irrational numbers are decimals, so they fall in between the whole numbers. When the first number of the decimal portion of the irrational number is less than 5, the tick mark made on the number line should be closer to the whole number part of the irrational number. Let's have example number 2. Arrange square root of 15, square root of 9, and square root of 3 on the number line. Now, let's use this number line. The approximate principal roots of square root of 3 is 1.73, and it lies nearer to 2, while square root of 9 is exactly at 3, and square root of 15 is 3.87, thus it lies nearer to 4. Example number 3. Arrange square root of 6, 15 over 4, and 0.65 on the number line. Now, let's use this number line. The approximate principal roots of square root of 6 is 2.44, and it lies nearer to 2, while 15 over 4 is 3.75, and it lies nearer to 4, and 0.65 lies nearer to 1.
Now, are you ready to answer your module? Good luck!
What's more? Independent activity number 1. Turn your module to page 15. Choose the letter of the correct answer from the given choices. Independent assessment number 1. Turn your module to page 15. Circle the number in each row that is not a perfect square. Independent activity number 2. Turn your module to page 15 and circle which number is greater. Independent assessment number 2. Turn your module to page 16. Identify which among the given radical numbers are perfect square. Put joyful emoji if it is a perfect square root and a sad face emoji if it is not a perfect square root. Independent activity number 3. Turn your module to page 16. Write C if the answer to the square root is true and F if it is not the correct answer. Independent assessment number 3. Turn your module to page 17. Estimate the square root of the given whole number to the nearest hundredth. Independent activity number 4. Turn your module to page 17. Place the given radical numbers below the letter that mostly accurately represents its location on the number line. Use approximation. Independent assessment number 4. Turn your module to pages 17 and 18. Choose from the given choices that represents the tick mark on the number line and circle your answer. Independent activity number 5. Turn your module to pages 18 and 19. Write T on the top of the tick mark if it represents a correct radical number, and F if it is not. What I have learned. Turn your module to page 19. Explain the process of estimating the square root of a whole number to the nearest hundredth. What I can do. Turn your module to pages 19 and 20. For letter A, evaluate the given word problems with square roots. For letter B, draw a sun if the order of radical numbers from lowest to highest is correct. If not, draw a moon. Assessment. Turn your module to pages 21 and 22. Let's answer our post-test. For letter A, estimate the square root to the nearest hundredths. For letter B, identify which two consecutive integers does each radical number lie. Put a box on your answer. Additional activity. Turn your module to page 22. Place each number in the correct area of the Venn diagram. References.
Study time! It's time for you to enter your module.